So yeah, I'd like to speak about higher order convergence rates within numerical homogenization, which is a topic I started to work on some time ago, and which is still interesting to me because there's still new stuff that pops up that makes things better or things to explore. So I'd like to convince you that this is actually interesting. And well, I skipped the slide with the motivation about multiscale problems. I mean, we've seen that a few times this week, and I will directly start into the model that we're interested in. So we start for the moment with the diffusion equation. So we've seen that a few times as well, with some heterogeneous coefficient that is L infinity and probably very oscillatory. And just for convenience, I will assume that there is some scale epsilon on which this coefficient might vary. That's not necessary, so we don't have any assumptions on the scale actually being there, but it makes things easier to understand what's going on if we have actually a smaller scale on which things vary. So we know quite classically in finite elements, so assuming now that there's maybe some higher regularity for the coefficient and domain maybe as well, quite classically I can write down a first order estimate going through H2 regularity of my solution. So that would be a result like this. It's here. And I've indicated this here already. If my coefficient is somewhat oscillatory on some scale epsilon, there will be some epsilon dependence popping up. So in particular, like think of some smooth coefficient that is oscillatory on the scale epsilon, then this here basically is something like 1 divided by epsilon, which is of course not very good if you want to approximate on a rather coarse scale. And we see this quite nicely here for this in this plot. So this is the standard finite element approximation, first order, for checkerboard coefficients. So I took coefficients that take two values, so there's like white and black squares, and the black squares have value 10 and the white squares have value 1. And then we see if the epsilon is rather coarse, so we just have 2 by 2, then there's, or 4 by 4 even, then we see the nice convergence behavior of finite elements as we would expect. But as soon as we make this pattern smaller, so we decrease this epsilon scale, and we see that there's this stagnating behavior. So we make the mesh size smaller, but things don't get better. And I mean, here we see nicely how it depends on the epsilon. So if like epsilon is decreased by factor 2, then it takes one additional refinement to get to the point where the convergence starts. And I mean, this is of course a coefficient which does not fall in this category where I can actually write down something explicitly here because I don't have the regularity, H2 regularity here. But still I see this kind of effect that there's some epsilon dependency here. Okay, and that's exactly, I mean, we have seen this a few times this week where numerical homogenization kicks in. Yeah? So the idea is that we design some coarse space and some coarse approximation that in H1 gives us a first order result. And the important thing is that it's independent here of any epsilon. And I've illustrated this in this picture here with the LOD method that we've seen also a few times this week already, how this might look like. So we construct this space with all the corrections and stuff. I will get to the details later on. And then this is what we see. So more or less independent of the epsilon, I see a first order convergence behavior, and actually it's slightly better. So I will comment on this later on why it's maybe a little bit better than first order, and that's exactly what will be important with the higher order than in the end. So towards the end, it seems to stagnate a little bit for the smaller epsilons. This is related to the fact that I chose a quite small localization parameter, and I would have to increase that, and then I would see basically that all these things behave more or less the same. So it's possible to do something like this, and in the error estimate that I will put again, so we had this on Tuesday morning, but I will put it up again because you want to like find out where we can actually squeeze out more orders if we want to go to higher order. But for the moment, this is like the state of the art, what we have in classical numerical homogenization. And what I want to achieve is something like this. So I have H1 and then some appropriate space or some coarse function in some appropriate space such that I get out some higher orders in whatever. I have to find out where to get them from, but it's clear that there will be some dependence on the regularity of the right-hand side. So I have to invest something. And we also know from finite elements that something like this goes through regularity of the solution and maybe the domain, and in our case also the coefficient. So there's an intermediate step where I take, so I know that this is some quasi-best approximation. So I can just take an interpolation into the space. If I take finite elements here, so into some space of higher polynomial degrees. And then I can use interpolation estimates. But there, of course, to get the higher orders, I have to invest higher derivatives of the solution as well, which then I can bound again by the right-hand side if it's regular enough, but I have to go this step through the regularity of the solution, which is, of course, a problem in my case, because, so, I mean, let's think of piecewise affine, piecewise constant coefficients, like the checkerboard one. So what I can assume at most is like H1 and then maybe a little bit more, but I will not be able to go to H2 in a very general case of jumping coefficients. And what I need in the finite element context to get results like this are regularity assumptions on domain, solution, and in my case, the coefficient. So there's some mismatch, and I try to like find other ways to extract higher orders. So that's what the talk will be about. And well, to start, maybe I'll put up some references, because it's also nice to see with whom I've been working on this. So I started some time ago to invest these higher order things. And then there were some things left that were not optimal or to improve. And basically, in terms of localization, it didn't work out nicely in the first work. And then in the elliptic setting with Jean Dong from INRIA in Paris and Moritz Haug, who is right now a postdoc with Axel, we managed then to improve the localization a bit, also in the elliptic setting. And then we started to move this to time-dependent problems. So that's what I did with my PhD student, Felix Grumbiegel, where it turned out that it doesn't work as nicely as expected in the very beginning. And there's a reason for that, and I will present that. And we now recently figured out how to improve these things and make it actually higher order in the time-dependent case as well. And that's an ongoing collaboration with my PhD student as well, and Xiang Wang from UMIO University and his postdoc Balache. So Balache was actually trying quite a bit with numerical experiments to figure out how to do it. And then at some point he had some nice experience that like opened the way for me to prove everything nicely. So that was a nice collaboration here, which is still ongoing, so we're writing the paper right now. All right. So let's go to the model problem for the moment. So essentially the way I wrote down the papers is also the way we will go through this talk. So we start with the elliptic setting just to understand where to get the higher orders from. And then we move to the time-dependent setting. So this is the setting that we've seen a few times this week already. So we have this Pauli form A that includes the coefficient and then the gradients. And on the right-hand side we have some function f in the L2 scale program. So that's very classical. And again, the A might be something highly oscillatory. So here are some assumptions that I pose. So in particular, A is only L infinity, so I will not assume any more regularity than L infinity on the coefficient. And just for convenience, I will just assume that A is scalar valued. We have seen in a few talks that this is of course not necessary. We can go for matrix valued coefficients as well. Not even symmetric, it's also not necessary, but then things are a bit more tricky. But we'll just stick to this scalar case to make things a little bit more easy. And A is possibly very oscillatory, so that's the important thing. Everything works as well if there's no oscillations, but that's of course the less interesting part. And again, for convenience, I just assume that A is piecewise constant on a very fine mesh. Right? That's not necessary for the theory, but it again helps to understand on which scale things are actually going on. I also need assumptions on F. So quite classically in numerical homogenization, I would just assume that F is an L2, so that's like the minimal thing that I need to get at least one H out. And in my case, we will need possibly higher regularity that is only local. And so there will be the coarse mesh on which we operate, and we will need higher regularity of F, so the right-hand side, with respect to the coarse mesh only. So that's a very basic setting, and now I would like to first talk a bit about existing approaches and what are like the limiting factors here. So there's of course approaches in connection to multiscale methods and numerical homogenization where it's about designing higher order methods as well. So I've listed a few, so there's ones that are based on HMM or MSFM, so in these contexts there's often like some assumption on an existence of a homogenized solution, which then helps of course, because then the homogenized solution is typically more regular, and this can be helpful to then get some higher orders out of there. And then there's hybrid approaches like the multiscale hybrid mixed method, multiscale hybrid high order method, and what Gabriel actually presented yesterday, multiscale hybrid method. So these things, they're also able to achieve higher orders, but they come with some assumptions. So we need some assumptions on either of these things. So maybe not all of them, but at least some of them. So in these cases, for instance, it's helpful to have a smooth homogenized solution. So I need the solution, so the homogenized solution to exist, and then the regularity is not that big of a problem anymore, but I need basically the setting where a homogenized solution exists, which is not necessarily the case in a very general case. And at least I need piecewise smooth coefficients in most of these cases. I think Gabriel also mentioned that yesterday, that he needs, so things can jump on the coarse element boundaries, but not within the coarse elements. Yeah. There's assumptions that you need, and I will try to convince you that you can get higher orders without all these assumptions. So I just want to assume some regularity on F, L infinity on the coefficient, and these spectral bounds or upper lower bounds, and that's about it. Yeah? So that's what I want to assume, and I want to get the higher orders just by appropriate construction of the multiscale space. All right. So we start off with our well-known method, localized orthogonal decomposition. So I will go through the main steps here. Just, I mean, it's some sort of a repetition because we have seen that before, but basically we will try to boil down where we can try to achieve more than what we have right now with the localized orthogonal decomposition method. And I think it's nice to, since it's Friday morning and everybody's a little bit tired, to just go through things again. So we have a mesh. What's mesh? Quasi-uniform, that's the easiest case here, and I have a first order conforming finite element space on that mesh. So I will, in this talk, mainly consider quadrilateral elements. Everything works as well if I go for simplicial meshes, but it makes things a little bit easier if I have the tensor product structure. But it's not a restriction, just that you know that I think of tensor product elements here. And then I have a local projective quasi-interpolation operator with local approximation and stability properties. So there's quite a few properties that I put in this small sentence. So it's important, it's an operator that maps from L2 to my finite element space, which has a few properties. So it should be a projection, that's what was written here. And it should have approximation properties in the sense that if I take a function and I subtract its interpolation, that this in L2 can be bounded by an h and the gradient of the function. And then here also the term local comes in, so this should happen locally. So essentially I want an interpolation operator or cross-interpolation operator that does not smear out things too much. So essentially, if I take something that is local, it should stay rather local. And the second thing I need is stability of this operator in H1. All right, and then we have seen a few times, so the space in which we then want to construct corrections is this fine scale space or detail space W. So we take the kernel of this interpolation operator, and then it's actually quite easy to see that you have these coarse contributions from the finite element part, and then you have the rest, which is in this detail space. So together they make up the space H10. All right, what is done then? So that's the ideal construction for basis functions. So it's actually the orthogonal decomposition without the localized part in it yet. So we have an operator mapping from H10 to this space, and it's basically a projection into this fine space. So we seek a function in this W space that solves this equation for all the test functions in this space. We've also seen a few times that you have to do some adjustments. So this is, you have to localize that at some point, and you have to discretize it at some point. We'll just neglect that for the moment and stick to this optimized setting for the moment. Well, and then it turns out that an optimal space for approximation in terms of numerical homogenization is this space here. So we take the functions in this finite element space and we subtract their corrections. And by construction, this is a space that is A orthogonal onto the functions in W. So that's the A orthogonal complement of that space in that sense. And this space is optimal in the following sense. So if I compute the Galerkian solution of that, so I mean I take tests and ansatz functions in exactly that space, then the function that I get out from this procedure fulfills this property here. So I get this nice first order convergence behavior, and that's independent of epsilon. So that's what we have seen before, and now let's have a look again into the proof that we have seen on Tuesday already. where things maybe go wrong with the higher orders, or where we can invest something additionally to get the higher orders. So that's my favorite proof, right? I start with Galerkin orthogonality, which is kind of essential here. That's of course classic, right? It doesn't really matter what kind of subspace I take. I always have this property that if I take the solution, I subtract this solution in the subspace, and I test with functions in that subspace that this is 0. But in my case, this is a very nice feature because it tells me, because we have this A orthogonality of the spaces, that this error between these two is a fine scale function. So it has interpolation 0. And that's something very important in the proof. And then, of course, so that's basically what my operator brings. By definition, I have interpolation properties, so that in L2 the error is bounded by some h and then the gradient. And as I said before, I want actually to work with a local operator, so where these things hold in a local fashion. So I put some element here and then maybe some elements and some patch here. But for the proof, it's enough to just have this global estimate, which of course follows from the local. Now this is the standard proof. So I start with the lower bound of the coefficient and my H1 semi-norm. I can bound this by the bilinear form. That's very classical. Then I use my Galerkin orthogonality to drop one of these terms. So here, of course, I also use symmetry. And then here I'm at the point where, well, this is my solution. This is a valid test function in H1 0. So, well, I can just go to the right-hand side. And now what is here typically done is, I subtract the interpolation operator. Why is that possible? Well, the interpolation of the error is 0, so I can just subtract it. And now this is essentially the proof. So now I can, well, just bound this in L2. And if I look at this here in L2, then I can just apply this estimate here to get out 1h and the gradient here of the error, which then I can just subtract with one of these, or divide by one of these. So that's the classical error. And you see, I mean, there's not much happening in total, so there's also not much room for improvement. There's more or less exactly one point where I can do something, and that is here. So well, here everything is equal, and then at that point, so it's not clear if this is actually possible in the case that I have here now with the classical LOD, but that's the point where I can start. So I want to subtract something here, which is not problematic because it should be somehow orthogonal to what I have here. So that's like my aim. So that's the idea to extract something here. And that's probably also what happens in the classical LOD case, that the order is slightly better than 1, because most likely you can subtract something here, at least for very nice right-hand sides, that gives you some half order or something. I didn't manage to prove that, but it feels like that. And in my case now, so when I look at this, it seems like the optimal interpolation would be the L2 projection. Because if I have the L2 projection here, I can subtract the L2 projection here as well, because then this is something whose L2 projection would be 0, so I can subtract here something in that space as well. Because if we're in L2, that would be the optimal fit. And then in this, so say IH would be the L2 projection, and I can at least extract another order from this thing here. I put the L2 projection here as well. But there's a problem with this. It sounds good maybe to take the L2 projection, but we have the problem that the L2 projection is not local. If I project into the finite element space, this is something global, in general. And this goes against my assumption that I want locality so that I can localize my basis functions at some point. So that's of course a problem. And we try to resolve that now. To like change everything in a way that we can use the L2 projection and do not suffer from locality, or not having locality. And everything starts again from the classical LOD, so these are the standard references, and in some sense also the gamblets, which have been introduced by Newman and Vardy, play a role here. So there's some connection between these two methods, and I like combine ideas from both of these in the construction. So the observation for the classical LOD is the following. So let's say I have a basis of my finite element space, where I can just choose that very classical head functions. And now if I compute the optimal basis function, so the one where I haven't localized yet, then I can get them actually by an energy minimization problem. So energy is here just this A linear form, putting V and V here. And then this is the minimum, or the argument that minimizes this quantity under all functions in H10 with the constraint that the interpolation of my function is exactly the one of the head functions. So that's the constraint that I have here. And with this fashion, I can directly get a basis of this optimal LOD space or OD space, however you want to name it. And the nice thing with this formulation is that this is just a constraint, so it doesn't really matter what I put here. So in the classical LOD, it's important that there's conformity. Here it's actually not important. It's just some constraint, and I have to make sure that this constraint is somehow reasonable. I could put some crazy constraint, but I won't find any function, so that's a problem. But if I put some reasonable constraint here, I could also put like a constraint that I take the L2 projection here onto piecewise polynomial functions. Why not? It's possible with this formulation. And that's exactly what we will do. So we start again with our mesh. So that's the very same thing as before. And we fix some polynomial degree. And then I take a non-conforming space, EHP. So I have my mesh and I take, so in my case, because I have tensor product elements, it would be, typically I take as basis functions Legendre polynomials in each direction, and I just multiply them to get some tensor product functions. And that spans up the space of functions that are polynomials of some certain degree in each coordinate direction. And so I get, on each element, I get p plus 1 to the d basis functions here. And now in this setting, I can easily use the L2 projection, because this is a local operation. There's no communication between the elements. So if I take the L2 projection, this is exactly local thing. And that's what I want to exploit here now. So I set up my multiscale space, more or less as before, now just with this new space, starting from the new space here, the polynomial space. So I take the span of some newly computed functions for all elements and all the indices within an element. And again, I take just the argmin of the energy here with the constraint that the projection is equal to one of these Legendre functions. And of course I can write that down. I have to prove somehow that this is not an empty constraint and there's some sub-conditions to be fulfilled, but this works out nicely in that case. And just for illustration, how such a function would look like, so if we have p equal to 2, some function, then it would look like this. I mean, we all know these classical functions from LOD, and here we just have some more oscillations going on. And we already see that there's some sort of decaying behavior. So the plot here is somehow logarithmically scaled in terms of the color coding. So quite quickly things decay. So that's already quite nice to see. And what is very important, and it's essentially the same thing as we get for the LOD, but it's a bit, you have to do a bit more to see that, is that the Galerkin solution that you compute in this new space fulfills now that its projection into the polynomial space is equal to the projection of the unique solution, or the exact solution from which we actually want to approximate. And that's again a feature, similarly to the LOD, where we had IH of the error is equal to 0, and now it's like pi of the error is 0. But that's exactly what we want to use in our error estimates. So let's have a look into that. So I said that's my favorite proof, so we'll just repeat that a few times. So we start again with the very same thing. It's again a Galerkin procedure, so I can plot this one thing. And now, well, I move to the right-hand side. That's exactly the same as before. And now I'm at the nice stage that, well, I can subtract the L2 projection here, because the L2 projection of this thing is 0. That's what I just mentioned on the last slide. But I can also subtract the L2 projection from the right-hand side, because of these orthogonality properties that are now built in by the L2 projection that I use here. So that's quite nice, because I mean I can assume a regularity of the right-hand side without assuming regularity of my solution U. So essentially, I can extract, say, p plus 1 orders here if I'm willing to invest p plus 1 derivatives of f. And here I just get one h, that's more or less the classical thing that you do in LOD. So you get h to the p plus 2, and then some constant that also scales nicely with p, so 1 divided by p faculty or something like that. And then I again divide by the gradient, and what I get out is such an estimate. And it's quite nice that this can be done without any regularity assumptions on domain or the solution. So I just extract this from the right-hand side directly, and somehow it also fits to classical finite elements in terms of orders. So for classical finite elements, well, maybe I would have the full domain here, but if I invest h p plus 1 here in f, then I would have needed u to be in h p plus 3. So, and then it would be like very classical. So in that sense, like the orders fit to what you would expect from finite elements, but now we're in the multiscale setting and it seems to be the right thing in terms of the orders. All right, so that's nice, but of course this is not practical because everything is global, right? So we have to globally define these basis functions in the way I did it. So again, there is an exponential decay that is important and some localization that plays a crucial role. And well, essentially one can show a similar proof as for the classical LOD that there's some decaying behavior of these basis functions. So let me just illustrate that quickly. So we start from one element k, which is the black one here in my case, and then I take away some layers of element around this. So let's say if L is 1, then I would take this away. And then the basis function that I started from on this element k, if I just look at this on the outer part, so the white part, then this will scale exponentially in L. So if I increase this by one layer, then there is one given factor by which the error decreases here. And that's exactly the exponential decay that we typically have. And now flipping this means that essentially everything is captured in a given patch. So now this is the only time I speak a little bit about discretization on the fine scale. So what you do now, of course, you have to solve these constrained minimization problems, which you can do by transferring it to some saddle point problem, so that's not a big issue. But of course you do that on some fine scale. So you take this patch, you make it, you discretize it on a fine scale, and there you actually solve these problems. And in our case, we just use P1 on the fine scale. So if the fine scale is fine enough, that's not an issue. And I mean, anyways, we don't have much regularity. So on the finest scale, we need to do something very basic. And so so you could do something else, but I think you cannot expect to make it much better in terms of convergent behavior on the fine scale. All right, so this has to be small enough, and of course it also depends on P. I mean, you can imagine if you have some basis function in your original space of order P, then there's some oscillations going on and you have to resolve them. So compared to what you have for classical LOD, there's always like a factor P that you have to consider as well to resolve the oscillations. Yes?
What's the relation of little h and epsilon?
Well, essentially, so if you write it down, it would be that h needs to be smaller than h times epsilon divided by p or something like that. So that's what, yeah, kind of. But if we compare to some finite element discretization, then I mean, this term always drops. But it needs to be small enough. That's quite clear. All right, and then of course, well, we don't only do that for one patch, but we have to do it for multiple patches. And if there's some redundancy in terms of the coefficient, we can exploit that. So that's pretty standard. And then, well, in my case, the localization now requires L to be larger than log h, well, to get some h out of the exponentially decaying term. And it's also clear that there needs to be some p dependence, because I don't only want to have an h. When I look at the localization error, I want to get h to the p plus 2. So the p dependence will be there. So it means that localization, or the patches need to be larger, of course, to capture the additional rates. All right, so that is what we get. And just for illustration, if we look at the decay properties of certain basis functions, it's exactly how we would expect. So say we start with the polynomial degree 1, then there's an exponentially decaying behavior if we increase the localization behavior. So if you take away more elements in the patches. And kind of we already see here that if we increase P, it seems to get better. So if we basically don't change the localization parameter, then increasing P could still reduce the error. That's not what we see in the theory. That's actually flipped. So the theory suggests that the P needs to be always larger. So with P, also the patch needs to increase, so say like this. But in practice, we always see that it's the other way around. So the P has a positive dependence in terms of the exponential decay. So we also see that here. So if we fix some certain L, so that these different lines are fixed L, then maybe not much, but slightly with the polynomial degree, stuff increases, and then we see that there's some stagnation at some point. But at some point, we're also maybe too close with our finest scale, so that could also be a reason for this stagnation here. Okay, so that's the illustration of the decay behavior. And then the localization is rather straightforward because everything is already local in a way. So if I look into this minimization problem, so we had the argmin in the whole space. So what I now just do is I restrict this to a patch. So I just do the minimization in H10 off a patch. That's the easiest thing you can think of. And well, the problem is this. I can write down the practical method in this new space, setting up by these basis functions here. But the Lurkin method is not optimal in a certain way, so this localization strategy is not perfect. And you'll see that here in terms of the error estimate. If you look into the error estimate, you will see you get one term, which is essentially what you get from the ideal method, and then you get this exponentially decaying part, and there's an h to the minus 1 here. So that's what they had in the very first iteration of the LOD method as well. And that has the effect that if I don't increase the L, then my error might go up again with decreasing h. So that's not optimal, of course. I can always kill this term by having like large enough L so that I get, instead of h to the p plus 2 here, just h to the p plus 3 and cancel the term. But in terms of practice, it's of course not optimal to have this iteration with h. So that's what I get with this direct localization. But there's a small thing that you can change to get rid of this h to the minus 1. And there's a few works that have led to us using this approach. The first thing is, I have mentioned that before, the LOD is based on conforming spaces, which I have now lost with having these piecewise polynomial functions. But I try to go back to the LOD setting by making it conforming. And I do that by bubble functions that are certainly constructed in a certain way. So I set up a space that consists of functions that are in H10, and actually, I should have been precise here, each of these bubble functions should be locally supported in some way. I wrote local here, so okay, it's included somehow. And I want to have them to have the property that if I take the L2 projection of them, I get out one of my original basis functions. So there's like a 1-to-1 correspondence between a bubble function and the corresponding Legendre type polynomial. And this has already been used in the lowest order case in a work by Michael Feischl and Daniel Petersheim some time ago, where they like connected ideas of gamblets and the LOD by using such things to introduce such bubbles in the lowest order case. But you can do it in the higher order case as well, as we will see. So what we can do now with having that space is we can take the basis functions here and compute very classical corrections for these functions. Because now we're back in the business that we have H10 as the space where everything is contained. So there I can write down my corrections as we had them before. So I can project them into a fine scale space, which is now the kernel of the L2 projection restricted to H10 functions. So in essence, then what I get is a space 1 minus C UHP. So that's the bubble space. I correct it. And by this construction, I get exactly the same space as I did with this constrained energy minimization. And it's also somewhat the connection between gamblets and the LOD in that sense. Now the problem is, again, this H2 minus 1, as I said, and there's like one slight thing that you have to change to make this work. And that has also been addressed in the actual Numerical paper by Robert Altmann, Patrick, and Daniel, and has then been used also in the lowest order case by Moritz Haug and Daniel Petersheim in terms of some multi-resolution LOD. And we have then picked that up for the higher order case in the very end. So the point is, you need some special localization, and you need to replace the constant polynomial by something else. And well, the nice thing is we already noticed it doesn't really matter as long as the L2 projection is what we need. So we need some function whose L2 projection is the piecewise constant. So we have this L2 projection here, the piecewise constant function in orange. And then for the lowest order case, so if p is equal to 0, that would be the optimal function here, the blue one. So if I project, so if I take the L2 projection of this whole thing, then it will be 0, and that part will exactly be the orange thing here, and then 0 again here. But it's slightly extended. And what you can do with this function is you can compose it of local bubble functions and, well, some linear part. So essentially this function is composed of a function that looks like this. So a linear function with 3 contributions, and then local bubbles that look like this and this. And for these, you do different localization strategies. And so for the linear part, you do what you do classically in LOD. You cut it into the element pieces. For them, you compute the corrections, and then you glue it back together. And for the bubble parts, you just do what we did before, this like straightforward localization where we just localize it based on this one element and a patch around it. And this is what does the job. So we can prove that as well, that this curse, this H2 minus 1 that is there, And it's quite interesting that you only have to do it for the 0th order basis function. And for all the others, you can do basically what I did before. It's just this one thing that you have to correct. So it doesn't really matter much in terms of complexity. You have to be a bit careful because if you go to higher orders, these bubble functions, they look slightly different. But you only need it for the lowest order case, so you solve some linear system to get the optimal bubble function there, and then you're set. So it's not complicated. So let's illustrate that here. So in the very beginning, when I did not do this special localization, and this is the result I got. So I just have here 2 cases, p equal to 1 and p equal to 3, just so that the plot is not too crowded. The other cases are also considered, and you can find it in the paper. So essentially, if L is large enough for p equal to 1, we get here order 3. So that's that line here. And if we say we have p equal to 3, then we see here nicely that we get 5th order convergence behavior. Up to localization effects, of course. And here, if we don't do this special localization trick, we will also see at some point it goes up again. And if you put the line there, you will see it's h to the minus 1. Well, if I do this special localization trick, then this is what I get. So I at least don't deteriorate, so it will stagnate. Of course, the L has to be large enough to cover for my higher P and stuff, but it will not deteriorate. So that's a nice improvement with just some neat nice trick. All right, so that's what we can do in the elliptic setting. And as promised, I wanted to go to some time-dependent case. So actually, we started to look into that for the wave equation. But it works more or less the same for parabolic problems as well. And then, well, we decided it's easier to start with one time derivative and go to the second one later. But essentially, the ideas translate. So we have a parabolic multiscale problem now. So essentially, we have this term that we had before, but we now include the time derivative of u as well. So u is now in the following always a function that depends on time and space. And of course, f as well. And a is a coefficient that only depends on space as before. Has these upper and lower bounds, it's only at infinity, basically everything as before. I fixed very simple initial conditions here and boundary conditions, but that's not restrictive. It just makes things a little bit easier to just start with this. And then, of course, what is interesting for us is then going to the weak formulation and working there. So weak formulation is also very classical. I just multiply with a test function, do some integration by parts here, and then this is an equation that needs to be fulfilled for every time. And now, well, I could just naively say, I have now this nice high-order method in space. I'll just apply it to this problem. So I can construct a space as before, based on everything that's elliptic. That's typically what you do. And I plug it in here as test and ansatz functions. Of course, to make this fully practical, there needs to be some localization again, which I will skip for the moment, and also the fine discretization. And there will also be some time discretization, of course. But we'll just neglect that for the moment to see the essential effects. So let's see how this method here performs if I take some very fine time discretization. So what I get out is this here. So I will see, as expected, for p equal to 0, I get plus 2, and it's always p plus 2. So I get second order behavior. For p equal to 1, I get third order behavior, and then I see this weird thing here going on. So somehow, if I increase the polynomial degree further, there seems to be some threshold where I cannot get better. If you look closer, you will see that this is second order. So, okay, you might think, well, the time discretization is bad here, right? So I just chose something where the time discretization will kick in at some point. But that's not the case. I mean, I can take any time discretization, can make it as fine as possible. There will always be this picture here. So let's try to understand what's going on here, why that happens. So we go back to my favorite proof. So we want to find some area estimate now in this time-dependent setting. And, well, to make things easier, we just assume that in each time step we have the perfect function in our space. We project it each time into the higher order multiscale space. So I have some projection onto this space, which I call P, and essentially this is just for a given point T, taking the function that I have there. So of course, this is the exact solution that I don't have, but that's just for theoretical purposes to understand what's going on. And I take 1 minus c of this. So that would be the projection in each time step. And then, in particular, I see that I look at the error. So that's basically what we had in the elliptic setting all the time. The error between the solution and this projection is now just c of u. And this is, again, something in my fine scale space, which is always something that is nice to have in this very classical area estimate. All right, so let's try to use that. It starts as always. Now it's slightly different here at that point. I don't use Galerkin orthogonality because that's not the Galerkin solution. But, well, I know that u minus pu is just cu, so I plug that in. And now I know that this is the correction, and this is a fine scale function as well, so I can just remove the c. So I have u of u minus pu. And then again, I can apply my equation. Right? But now the problem is that I don't only have the right-hand side, I also have this time derivative. So that's what we get here. So I get the f, well, and I get the u dot. I can still just try to do what I did before, naively. So I subtract my projection here on the right term for both these terms, so that's not an issue. I can get 1h out of that, because I don't have more regularity of u. So here I can get whatever I want, well, up to p plus 2, p plus 1, and then the other one comes from the second thing. But here I'm stuck. So now I again have projection error of u, and my u is of course not regular, so I cannot expect much more than h1. So I have this nice high order method that is not high order. So it's a bit of a problem. So this is essentially where we see this cut with the second order. So it's exactly as in the numerics. So we get some high order terms, so we of course then divide by this term again, but this is the dominating part. And well, if my solution is more regular, maybe I can get more h's out of here. But I'm essentially done here. So it's second order, and that's it. And now if we go back here, well, maybe you noticed the red curve is third order. But that's probably because there's two terms that like two different error contributions. And I guess that in the very beginning, this higher order term is somehow the dominant part. And then at some point, there's like this, you see that here nicely, threshold where the second order term seems to kick in and then dominate the error behavior. All right. So yeah, can we get rid of this problematic term? So we tried some stuff, and so what I will show you now is first of all purely theoretical, and that it's not practically relevant, but it led up to something that is practically relevant. So that's why I show it. So well, we are working with corrections here all the time. So why not just remove the problematic term by defining some ideal correction that does its job? Well, just disclaimer again, we're in this non-localized setting without any discretization on the fine scale yet. So that's just to figure out what's going on. So I define a correction that is now D because it's the letter after C. And it maps again to the fine scale space, and it solves something that looks very much like a corrected problem as before, but with the difference that I have L2 now on the right side. And somehow this seems to be the right thing, as it will turn out. So what I do, so I call this enriched projection. So I take at each time step the projection into my LOD space, or this higher order LOD space. And then I still subtract some contribution from this D and the time derivative of U. So as I said, this is not very practical because I don't have the time derivative of U, and I don't have U either. So just to like figure out in what sense my space is not optimal. Because I mean, with this projection error, we noticed that projection error is like the best thing I can get, or the projection is the best thing I can choose, but somehow it doesn't help me in this case, so that the space doesn't seem to fit well to the problem. And that's what I try to cure with this D. So let's get back to my favorite proof. Well, I put just the U minus my enriched projection here, which I can compute at any time step if I have a solution. Again, well, I go to the A, and then I split. So the error contribution is of course U minus PU, one part, and then there's this DU part, DU dot part here. Well, and then I continue. So remember, U minus PU is nothing else than C of U. That's the same thing as before. And C of U, because this is a fine scale function by definition, I can get to U and then go to my equation. And for that part here, I just plug in this, because again, this is a fine scale function, so I can use this equation here. And then it turns out that, well, I get my F, where I can subtract stuff as before. I get my U dot, again with this test function where I cannot do much, but I just leave it for the moment, and then I have this term, which in this corrected way just gives me exactly the term that cancels this. So it's very ideal and I mean very theoretical here, but well, in essence, I have removed the problematic term. So if I, like, in each step not take this projection, but put some additional thing to it, then I can get back my higher orders, only from F. Okay, purely theoretical for the moment. Let's leave it like this for a second and look at something completely different. I can write down my original equation in some coupled way. So that's basically the version of the multiscale method that I'm writing down here. So I know that my solution space, H10, is composed of this higher order space and this W space. So they add up nicely and are A orthogonal. So what I do is now I split the test functions as well. So I have, well, I say I have a contribution in this one space and this other space, and then I put in the first equation only test functions from this coarser space, and in the other equation I put the functions from the fine space. Nothing happens here essentially, and I can also like drop some terms because here's some orthogonality and here as well, so I can remove some terms even, but here it's nicely visible what happens. And now we can remember about this ideal correction D that we had before. And somehow it turns out, and I can actually prove that this is the thing that does it, that, well, okay, first let's say the problem with this equation is of course that this is coarse scale, this is the first one, but the second one is fine scale, yeah? So we operate on the fine scale, and if we discretize this with some time discretization scheme, I'm like on the fine scale in every time step. So that's the problem here. But as said, we remember this additional correction here, and what does the job is, I just replace this space W in this formulation by D of the LOD space. So I plug in functions of the LOD space for this V here, compute the corresponding corrections with the D. And then this is a space that has the same dimension as the space VH. So I essentially double the number of unknowns, but it's still coarse scale, and that cures my problems with the higher orders. To some extent, I will comment on that in a second. All right, yeah, so that's why this kind of theoretical thing here helped. And in the end, it boils down to having some sort of approximation properties where you try to. So basically, if you use this space, you will see that actually you wanted to have the full space, and then you have some error estimate between the LOD space and the full space, but it's after applying the D, so you get some additional orders out of that procedure. It's a bit tricky and like 3 pages to prove, so I will not do that now. Well, but we can see here that it does not work yet because that's still the old method. But now if I apply this, then what I get out is this. So it cures my order problems. There's some stuff happening here in the very beginning. I mean, it's smaller than before. But for some reason, it takes some time to get them the order in the lower order cases. But we see nicely that we get the right orders in the higher order cases. And you can extend this to some extent. All right, some comments on this. So this looks nice. Actually, it turns out that it's sufficient to do this decorrection with the lowest order space only. So I have the LOD space based on the piecewise constant functions only, which is of course then a space that has much smaller dimension than the one with which we operate. So that means if I have p plus 1 to the d functions in each element, then I just have to have, so I have p plus 1 to the d corrections as well, plus 1 for this additional thing. And well, essentially you would have to compute the LOD space anew for that because it's a different space if you take the p or the 0. But essentially you can just take the 0th order thing that you produce with a higher order space that works as well. So that's not much of a problem, just one additional correction. But of course that's limited to some point. So if I increase the polynomial degree even further, then at some point I will run into some stagnation again. But I can push this stagnation point further down the more corrections I have. So essentially it means, well, with this kind of technique I can get 4th order, and the threshold where it kicks in to get the 4th order, you can see it slightly here. So here it starts to get 4th order. So it's 5th until here, and then it starts to get 4th order here. And if you take high polynomial degrees, you will also see that it stagnates here. It doesn't stagnate, but like has reduced rate. So at that point, if you want to get even more orders, you would need to have an additional correction, which is again 0th order only. All right, so essentially it means you have the p plus 1 to the d basis functions that you compute anyways for the higher order space, plus something that is roughly p to the half that you have to compute additionally. And that's independent of the dimension even. So that's what we can prove. And well, okay, there's some stuff that we haven't done yet because this is very ongoing work. It's very recent results. Localization is quite promising, but there's of course a few things that you have to keep in mind. If I correct LOD basis function, and this is of course something that is not bound to one element, but already has some larger patch bound to it. So, I mean, I can either localize this to the elements as well, but then I get more corrections, or I compute the correction for this whole thing at once. And then the nice thing is that the function itself is already decaying, so I can expect to not take, so I have to take some more layers of elements to it, but not much, because the function itself already decays. But that's just stuff that we figured out in practice so far, and we have to make this rigorous how this actually scales with all the exponential terms that we have. But there's hope, yeah, that this is not a problem at like if that's with global or something like that. So that's not the issue here. Of course, what I have not talked about is like time discretization. So ideally, we just couple this then. I mean, we have this coupled problem, and you can take any time discretization then. So ideally, you just take something that is of the same order, some PDF scheme, or whatever. That's also still where to do the analysis, but so far this is very promising because it's actually what we do in the practical experiments. Now, last thing to say, I mean, similar idea. So the proof essentially works the very same way for the wave equation, but you have to do some other tricks. So it's a very similar idea if you have like 2 time derivatives instead of 1. And basically the overall result to more or less end in a second, so I have a conclusion slide, but I mean the overall result is that we can get higher orders, so a higher order method under very minimal regularity assumptions. So I just have assumed H1 in space, not more. And the coefficient is only in L infinity. Just by going through these additional corrections. All right, so let's wrap up. I've presented some higher order multiscale method, which works on a minimal assumption, as just said. And the orders that we get additionally in the elliptic case, they are just extracted from the right-hand side. And in the time-dependent setting, they are extracted from the right-hand side and by some additional correction procedure that we have to do, right? So particularly these additional corrections. And now what is like left to do is the proper localization. So it works with the localization, but we have to figure out in theory how it actually scales. And of course the time discretization to cook up the full proof with time and space discretization. Well, I guess that's about it. Thanks a lot for your attention.